Welcome to The Explainer. Today, we're tackling a massive challenge in the AI world, scaling few-shot prompting without losing your sanity. We're going to look at a fascinating method for efficiently finding the absolute best data to train your models. Okay, let's dive into this incredibly fascinating graph-based approach called VoteK. So if you've ever built a few-shot prompt, you know the absolute struggle this question represents. You've got thousands, maybe tens of thousands of unannotated data points just sitting there in your data set. How do you choose the perfect examples from that massive pile to teach your model? Let's be real. Frankly, none of us have the time, the budget, or the sheer amount of caffeine required from manual annotation of an entire data set. Sifting through all of that by hand, it's just a daunting, mind-numbing task. Enter our smart, automated savior, VoteK. It's a graph-based technique that efficiently selects the most diverse and challenging exemplars from your unlabeled datasets. Instead of you just randomly picking examples and, hoping for the best, this algorithm actually gives votes to the most unique data points. It completely removes human bias from the sorting process and relies on pure mathematical representation to find exactly what your few-shot prompt needs to succeed. Here's our roadmap for today. We'll be covering 1. The bottleneck, 2. Stage 1, finding diversity, 3. Stage 2, finding difficulty, 4. A practical climate change example, and finally, 5. Vocane limitations. Now, I know there's some dense graph theory ahead, but stick with me. I promise a clear step-by-step payoff. All right, section 1, the bottleneck. Look, few-shot prompting works brilliantly. By just providing a few high-quality examples, language models become significantly better at complex tasks. But there's a massive elephant in the room. Human annotation is a huge bottleneck. To find those few golden examples organically, you'd normally have to annotate a massive chunk of your training data just so you know what you're even choosing from. That is just way too costly and takes way too much time. We desperately need a system that can scan unlabeled data and tell us exactly which specific items are actually worth our time to label. Which brings us to section 2, stage 1, finding diversity. Now, what's really interesting about this first algorithmic step is how it systematically breaks down the search. Let's walk through these abstract math steps, because this is where the algorithmic magic really happens. First, VoteK computes vector representations of every single unlabeled sample using a model called SentenceBird. Think of this as turning your text sentences into coordinates in space so they can be compared mathematically. Once everything is a vector, step 2 builds a directed graph. Imagine every data point as a vertex on this graph, and the algorithm draws edges between them and their k nearest neighbors using a metric called cosine similarity. Essentially, it maps out local neighborhoods of similar data. Then, for step 3, we score the vertices based on dissimilarity. If a data point is too close to something we've already selected, its score drops. We want distance. Finally, step 4, we iteratively select the exemplar with the highest score, ensuring we're grabbing the most diverse, spread out points possible from our dataset map. Imagine you've got a bucket that represents your total annotation budget, which we'll call M. In this first stage, we're just starting to fill our bucket. We only dedicate a small slice, M divided by 10, or exactly 10% of our total annotation budget, to this initial diversity search. We're purposefully grabbing a small, highly strategic set of examples that are deliberately as far apart from each other as possible. We want the absolute broadest strokes of our data set right now. Moving right along to section 3, stage 2, finding difficulty. Now that we have our baseline diversity, we need to find the challenging edge cases. Here's how VoteK specifically hunts for those tricky examples. Step 1, we take that initial 10% we just found, we bite the bullet and manually annotate them, and then we use a language model to make predictions on all the remaining unlabeled data based on that 10%. Step 2, we rank all those remaining instances based on how confident the model is in its own predictions. And step 3, we do something that might seem kind of counterintuitive at first. We deliberately discard the top M over 10 easiest cases. We literally just throw them out. Why? Well, if the model is highly confident, it already understands those examples. Teaching it what it already knows is a total waste of time. Instead, for step 4, we select the next 9M over 10 lowest confidence cases. We are actively hunting for the tricky data points the model is scratching its head over. So the crucial point is how dramatically skewed this budget allocation is. We've got our 10% slice dedicated to baseline diversity from stage 1, but a massive 90% of our budget goes entirely to the hard stuff in stage 2. We want to spend almost all of our precious manual annotation time on the precise examples that will truly challenge the model and force it to learn complex nuances. Let's look at section 4, the climate change example. Imagine you're an ecology student. You want to ask an AI about climate change on a very high academic level, and you have this enormous data set of climate change-related questions, but you have absolutely no idea which specific questions you should annotate to use as exemplars in your few-shot prompt. You definitely don't have the time to read through all of them, so you decide to let VoteK take the wheel and do the heavy lifting to find the most useful questions for you. The algorithm fires up stage 1. It compares all the text embeddings across your vast dataset, strictly looking for maximum diversity. Its very first pick is this question: how does global warming affect polar bear populations? This is an excellent starting point, right? It focuses purely on biodiversity and animal species. It sets a firm stake in the ground for one specific topic area. Then, because it's actively punishing similarity, the algorithm needs something as mathematically far away from polar bears as possible on the graph. It selects what are the economic impacts of transitioning to renewable energy sources. Look at how smart this is. The algorithm correctly jumped to a completely different topic, economics and energy infrastructure, to ensure maximum diversity for that initial 10% bucket. It's ensuring your AI sees the full breadth of the climate change conversation. Once that diverse stage 1 baseline is set and annotated, the model predicts the rest of the dataset and actively looks for those low confidence scores in stage 2. It pulls out this question: what are the social consequences of climate-induced migration? And this brilliantly illustrates why VoteK is so incredibly effective. Language models often really struggle with highly complex intersectional topics, like social consequences mixed with global migration patterns. Because the model wasn't confident in how to handle this, VoteK flagged it as a perfect, difficult exemplar worthy of your manual annotation time. It literally found the hard stuff for you. Finally, Section 5, VoteK limitations. Let's talk trade-offs. Because before we go entirely all in on this, we have to remember that as incredibly smart and automated as this algorithm is, it's not literal magic. It has real practical constraints. On one hand, yes, you get incredibly broad topic coverage using very few exemplars, which brilliantly optimizes your time. But on the other hand, calculating those sentence BERT embeddings and building directed graphs with k-nearest neighbors for a massive dataset, that is computationally expensive and requires serious processing power. Furthermore, it has a pretty significant blind spot. Volk prioritizes mathematical diversity, but it entirely ignores direct task relevance. A mathematically diverse exemplar might just be a bizarre peripheral edge case that isn't actually helpful for your specific prompting goals. And lastly, let's not forget, after all this fancy math, you still have to sit down and manually annotate those final chosen exemplars yourself. Which brings us to a final, provocative question to leave you with. Is prioritizing maximum dataset diversity always worth the risk of losing direct task relevance? VoteK is a wonderfully structured, mathematically rigorous approach to add to your prompt engineering toolkit, especially when you're completely drowning in unlabeled datasets. But you really have to weigh those computational trade-offs and the risk of irrelevant edge cases for your own AI workflows. Think about your current datasets. Where would a graph-based approach save you hours of manual sorting? And where might it just give you perfectly diverse but totally unhelpful examples? Thank you so much for joining me for this explainer. I hope this deep dive helps you build smarter, more efficient, and incredibly robust few-shot prompts.